For more than 100 years, physics has lived in this beautiful kind of tension. On one side, general relativity explains the universe on its grandest scales: gravity, space, and time. Now, on the other hand, quantum mechanics governs the microscopic world: probabilities, entanglement, and uncertainty. And yet, two theories, both dazzling, both true, and yet they don't quite fit together. Welcome back to Breaking Math. I'm your host, Autumn Fnaf, and today I'm speaking with Dr. Vlatko Vidral, quantum physicist and author of Portals to a New Reality, who believes that physics is about to undergo its next great revolution, not because of contradictions, but because of possibilities. Vlatko, thank you for coming on the show, and welcome to Breaking Math. How are you doing today?
Hi, very well, thank you.
Thank you so much for coming on the show. Now, looking at your book, you had one question in there and a couple statements. There's one thing that I have to ask. This gets really deep for quantum mechanics and quantum theory, and you stated the world exists only when it is not observed. What does that mean?
It's a great question, actually, and it gets to the heart of my view of quantum mechanics. So let me explain a little bit more. People frequently talk about quantum and classical mechanics in the following way. They would say, in classical mechanics, Newtonian mechanics, the pre-quantum mechanics, things existed independently of us making observations. So basically, if you measure a position of an object or the speed of an object, that object still has exactly the same position and the speed before and after your measurement. Now, interestingly, in quantum mechanics, and that's the way that you will hear most of the presentations actually speak about it, people say, well, things in quantum mechanics don't exist before you actually have made a measurement to find out what the true value for the position or for the velocity of an object is. And that sounds a little bit like what Bishop Berkeley said. Very famously, he said, if a tree falls in a forest, but there is no one there to observe that or to hear the sound, did it really fall? And that was, he was one of the biggest proponents of the philosophy of idealism, that ultimately it's all in our head, really, and things don't exist independently of our own observation. So I wanted to negate that. I actually thought that what quantum mechanics is telling us is the exact opposite of Bishop Berkeley, and I don't think anyone ever said that. So the opposite of this would be that, in fact, the full world in the full quantum capacity only exists when we don't observe it. It's exact opposite, I think, of this statement. And so what do I mean by that? What I mean by that is that this gets us to this really weird nature of quantum reality. So that actually in quantum mechanics, things like a position of an object or the speed of an object or any property you can hear, energy of that object, we don't represent them by ordinary numbers, by real numbers. So we don't say position of the object is 5 meters away from me. What we use is what I called in my book quantum numbers. It's the language that Dirac used. And these quantum numbers are really weird because you can think of them in mathematics as matrices. They are really tables of numbers. There are many numbers all given at the same time. And each property in quantum mechanics has this multitude of numbers associated with that. So one of the striking consequences, and that's what Heisenberg discovered exactly 100 years ago, actually, is that if you assign this quantum number to your position, and if you assign another one to your velocity, you will not be able to measure these properties at the same time. In other words, if you first measure the position and then the velocity, it's not the same if you switch the order of your measurement. So when you multiply two quantum numbers, it really matters which order you multiply them in. A times B is not the same as B times A in quantum mechanics. So that's what's interesting, that these quantum numbers exist everywhere in the universe. I think that's the best picture of quantum mechanics, unless you make a contact with the quantum system. And that's actually the central mystery in quantum mechanics. What happens when you make an observation? And in fact, what happens is that you end up seeing only one of these numbers. Out of this multitude of possible numbers, they could actually all be the position of your object. You pick out one of them, and your quantum numbers, so to speak, correlate to only one of these numbers. So that's why I said, if you let things be without any intervention, all of these numbers just simultaneously exist. However, if you engage yourself in the process of interacting with a physical system that you want to observe, you will actually only see one of these at a time. You can never see more than one, which led me to this negation of Bishop Berkeley, that the world only exists fully when we don't observe it.
I always find that to be a little bit fascinating because you can only see what is around you and not every other interaction.
That's it. That's it. It's very interesting. I think maybe one nice analogy would be if you take a die and you have 6 numbers on a die, but when you roll a die, you only end up seeing the top surface of the die. You only see one of these 6 numbers. But that doesn't mean that the other 5 numbers don't exist. It's just you're not correlated with the other 5 numbers. But of course, there could be another person who interacts with the same die in a different way, who is looking sideways and who sees another number. And actually, this is like a classical analog, if you like, of what quantum world is really like.
When you were diving into the book here and you were writing it, you've said that physics has been stuck with the same 2 theories for over a century. What are they, and what convinces you that we're finally on the brink of a new revolution? And what does that look like for us?
Yes, I think these are very important questions in physics. We've had 2 theories that describe, as far as we know at present, all observations that we can make, both in the micro, in the world of small things, and in the world of large things. One is quantum mechanics, and it did simply arise from trying to understand how atoms emit light. If you excite an atom, it will basically emit different frequencies, different colors of light. And more than 100 years ago, this wasn't really understood properly. Why only certain frequencies are observed, and why not the continuum of these frequencies? So it's the world of atomic physics, the world of objects that we cannot see. Slightly before that, Einstein came up first with special relativity and then with general theory of relativity. And this covers a completely different domain of the macroscopic objects. So he was really worried more about how gravity affects planetary motions, stars, galaxies even, and the whole universe. So it's right at the other end of the physical spectrum. And these 2 theories, not only did they start by addressing completely separate domains, non-overlapping physical domains, but over the last 100 years, they've only been tested in these separate domains. So we haven't found an experiment yet where both quantum mechanics and general theory of relativity would have to be applied at the same time. And in fact, even if we imagine such an experiment, there are of course many thought experiments where people think what would happen in such a domain. We actually don't really know mathematically. There's an extra problem. We don't know mathematically how to put together general relativity, which is incidentally a fully classical theory. In general relativity, we use ordinary numbers to describe all properties. All gravitational potentials are simply real numbers that are assigned to them, the SINA, classical numbers, as I call them in my book. Whereas quantum mechanics tells us that all of them ought to be somehow considered Q numbers, these tables of numbers. And we don't really know how to do that consistently mathematically. But it's even worse, as I said, because for us to even know which kind of mathematics to use and how to proceed in the right way, we would really have to first test things, at least in some domains, to see what nature really tells us about how to proceed in this way. So the reason now, to answer your second question, why I think we're on the brink of doing something really revolutionary and exciting is because now, finally, after 100 years of extraordinarily and boringly, I guess, successful 2 theories of physics, I think we're starting to get ideas how we could test jointly gravity and quantum mechanics in the laboratory. And that's exciting. And that's actually what prompted me to write the book, because I don't think that many people are talking about it. And it seems to me that the enormous technological development over the last maybe 3 or 4 decades has now put us in a fantastic position to address the question of quantizing gravity.
Our moment now to 1900, when Lord Kelvin famously declared that physics was complete, save
Yes.
for 2 small clouds on the
Yeah.
horizon.
Yes.
These clouds turned into relativity and
Yes.
quantum mechanics.
Yes.
What are today's clouds, and why do you think that most physicists don't see them?
Yes, I think that's exactly the question. I think, yes, Lord Kelvin was extraordinarily enthusiastic about physics, almost nearing an end at that point. He was very confident that maybe all we are doing is just improving the decimal places of our measurements and getting more and more accurate measurements, but actually the theory that we have is right. And the 2 small clouds, as you mentioned, turned out to be the 2 revolutions in physics.
But why does everyone think that whatever work they do is complete?
Yes, yes, it's a good point. In fact, already at that time, he should have been prepared to understand that surprises are the norm in science. And it's not entirely clear how he felt about these clouds, whether if you really pressed him and asked whether the experiments could go some other way rather than the one that classical physics would suggest, maybe he would have been open to that option as well. And I think we're in a very similar position now, because when you take quantum mechanics from the microscopic domain of particles of light, photons, atoms, where we've experimented extensively and we are confident that quantum mechanics is correct in that domain, even into simpler domains of chemistry, we understand the chemical bonding. It's really all about quantum mechanical forces between atoms. However, if you go towards more and more complex systems, not just gravity, as we mentioned in the macroscopic domain, but also living systems, then a number of questions arises, in fact. The first one, obviously, is would quantum mechanics survive that? Is it really valid, even at the level of living systems? Is quantum mechanics sufficient to explain life? So somehow going beyond the microscopic confines of quantum mechanics, where, like I said, we haven't had a single deviation over the last 100 years. And you could say the same about general relativity, but going in the opposite direction. So we are confident that large-scale universe really does behave according to how Einstein imagined it. However, as you make your object smaller and smaller, we actually have been unable to measure, for instance, gravity between 2 simple atoms. Gravity is too weak for us to even be able to detect that at present. So you could easily say, well, we don't know what happens. We don't really know if gravity is valid at that level where quantum mechanics is. And that's what makes me think that we have a number of these, I wouldn't call them small, but we have a number of clouds now where we can really test quantum mechanics. And you can already see, even from the physics community, that the topics are not settled at all. I think different physicists would bet, in fact, on different outcomes here. And as soon as
Of
you see this
course.
kind of controversy, that automatically to you as a researcher signals that that's the right thing to ask, because no one agrees on these things. So I think that, plus, as I said, I think we are technologically, because of the rapid development of quantum technologies, we are now really technologically at the level where we can test systems that are big enough to still control in a fully quantum mechanical manner, and also at the same time to be able to detect gravitational forces, for instance, between these systems, or to make them living and quantum at the same time. So I think probably sooner rather than later, within the next 5 to 10 years, we will have some answers to some of these questions that are raised.
Now, you've said that there are 5 thought experiments that we can dive into. Each one's kind of a gateway for the physics of tomorrow.
Yes.
What makes a thought experiment powerful enough to guide through genuine discovery?
Good question. One really never knows, of course. You only know after you perform that experiment. There is a lot of intuition that you have to use. Exactly as you said. Why am I focusing on these 5 experiments and why not on certain other open questions? There are, of course, thousands of open questions in physics that are not the ones that I discussed in my book. And I think as a physicist, you're simply using your intuition where you say, well, some of these questions are presumably more questions of understanding the behavior and the structure in more detail, but I don't really expect it to go any other way than the current quantum mechanical understanding. For instance, a problem I would classify in this way is high temperature superconductivity. We have
Yep.
superconductors at relatively low temperature, but we don't really know physically how to describe superconductors. We know they exist because we can make them, but we don't have a good theory that would actually explain them. It's a big open problem. It's been open for a long time now, more than 50 years, but you could in fact argue that this is really just a question of technology and understanding our technology properly. It's more like an engineering question and application of quantum mechanics. I really don't expect anything fundamental. I don't think that there will be a breakthrough in terms of a new theory really going beyond quantum mechanics or general relativity. So that's what you try to focus on. I think the most exciting questions are the ones where you think that our current understanding could in fact fail, but there is no guarantee here. There is always an element of surprise. So I think each of these experiments that I offer, I'm betting one way, and I'm very confident about that. I think that we will show that quantum mechanics does matter. Certainly, at least some aspects of quantum mechanics should survive in the experiments that I'm proposing. However, precisely because my expectations are in this direction, it would be far more interesting if these experiments failed for me, in
Right.
a way. It would be disappointing that I wasn't betting the right way, but in fact, it would signal to me that something is far more wrong with our understanding than otherwise, in a way. So it's a kind of win-win outcome. On the one hand, I think we could confirm that quantum mechanics really applies to the whole universe, and that in itself would be exciting. However, we could discover in any of these experiments that we have to go far beyond both general relativity and quantum mechanics. And of course, this will be even more exciting.
So, do you want to give a brief synopsis of each of the 5?
The 5 experiments, of course, are very crudely divided in the sense that they are very much related to one another. And frequently, the technology that you need is ultimately very similar because what you're trying to do is you're trying to maintain this quantum property of superposition, of being able to be in many states at the same time. It's just that what you're doing really is applying this to very different systems. So the first really experiment that I had in mind is to test this idea that observers, this again goes contrary to the prevailing dogma being the so-called Copenhagen interpretation of quantum mechanics, which says that you always need an observer to make a quantum behavior into a classical one. And that's what happens when you observe something. And like I said, my view is the exact opposite, that in fact, an observer is nothing but a bunch of quantum numbers. Observers are no different to other physical systems. As far as, of course, physical experiments are concerned, I think that's the best way to account for everything. And so the first set of experiments is to exactly test the quantum nature of observers. So I would like to have an experiment where an observer gets entangled, as Schrödinger predicted in famous Schrödinger's cat experiment. But I think my experiment would involve an observer, could be an AI system with which you could actually communicate, and you could probe the system to see whether they've made a definitive observation, and at the same time you could confirm that they are still fully part of a quantum mechanical state. So that's the first set of
Okay.
experiments that I have. It's probing the genuine, fully quantum mechanical nature of reality. Then I go to the second set of experiments, which are kind of these are steps we need to test before we get into the full quantum gravity. And these are experiments to do with time. they're fascinating because in quantum mechanics, when you couple quantum mechanics to our classical view of time, you get a number of really weird phenomena. So what I'm describing, for instance, is an experiment. This is a variant of Einstein's experiment with twins, where you have a stationary twin staying on Earth and the twin brother going on a journey to another galaxy, if you like, and coming back, like in the movie Interstellar, upon which the returning brother ends up being much younger than the stationary brother. They've done many experiments, and we know that this is correct in relativity, in classical relativity. And what I'm proposing is to couple this to a quantum superposition. So now I've got a single system. You can think of it as a single atom even, which acts as a clock. So you can actually count how many times the atom gets excited and de-excited. How many times does it vibrate internally? But what you do now is you make a superposition of a single atom. A single atom exists in two places at the same time. In one of these places, you take this atom on a journey and bring it back to the same location. So now you've got a single atom in a superposition of being younger and older at the same time, as it were. By time, I mean the time of the person conducting this experiment. So it's really weird that you can have these multiple references in quantum mechanics. There is one younger time, there is an older time, and there is a third time that basically depicts the time of the person performing the experiment. And so I go through all of these experiments that I think could be tested with the current atomic clocks. We just haven't done it, but in principle, we can do them with the current technology. And that takes me to the third set of experiments, which is to test fully quantum gravity. So if you have two superpositions of two massive objects, you put one massive object in two places at the same time and another one, the question is, can gravity quantum entangle these two objects? So can gravity create the state which we consider the characteristic? Schrödinger called it the characteristic trait of this is the state that has absolutely no classical analog in Newtonian physics. So if gravity could be the intermediary and could facilitate creation of entanglement, then according to me, that would actually be a witness of the quantum nature of the gravitational field. And it would be actually the first experiment to falsify Einstein's classical theory of general relativity. It would be the first, if it goes the way I'm predicting, it would be the first bit of evidence we would have to falsify general relativity and really tell us, yes, you must really treat it quantum mechanically like everything else. So that leads me to the fourth set of experiments. And as I said, this goes towards biological systems. So perform, mathematically speaking, interestingly, it's the same description as what I just described with gravitational objects. However, here you really want to entangle living systems.
Okay.
And this is a set of experiments that I'm also involved with in the same way as the gravitational experiments, where I would really like to show that living systems can be fully quantum mechanical and can be fully participants in this kind of what Schrödinger identified as the key weirdness of quantum mechanics. And this is because there are many views in quantum mechanics which claim that quantum mechanics collapses when quantum superpositions encounter living systems. So there are many people who subscribe to the view that everything in the universe might be quantum mechanical below a certain level. But as soon as quantum mechanics encounters living systems, then these people would expect quantum superpositions to collapse. And I think it's very important to test whether this is the case. And again, like I said, I would be betting against this. And I think it's an important experiment to do. And then finally, we have issue of even in the existing things that work really well, things like quantum theory of light, quantum electrodynamics, as it's called, we have degrees of freedom. I call them ghosts. And in fact, we call them ghosts. In physics, we call them ghosts because it seems to us they ought to be there. And it seems to me that they ought to be not just there, but quantum mechanical as well. However, the current theory tells us that they cannot be directly detected. So I have a
Okay.
certain set of experiments in mind, which you could call quantum ghost hunting or quantum ghost detection, which would actually claim that we should even go further with our quantum mechanical description, even of the theories that we think are well understood.
They're not just theoretical, they're technologically feasible today. So, what's stopping you from carrying them out now? And is that cost, imagination, or just something deeper?
Yes, this is a great question. Actually, to put it into the right context, it really is due to the rapid expansion of quantum technologies. So I think it started very slowly in the 80s and 90s when people could actually quantum entangle at most, let's say, two quantum particles. So you had two photons, and then everyone was confirming entanglement at the level of two photons. And now we know, of course, there are 3 Nobel Prizes given for this extensive work. Then people confirm this for atoms, for bigger molecules, and so on. But what all of these experiments led to ultimately is that the industry, the big industries like Google and Microsoft got excited about making a large-scale quantum computer. I think round about 2010, it became clear to everyone that this is no longer just a thought experiment, but in fact, there is a real possibility that we could make a large-scale quantum computer. And I think that's really what's required, because if you look at the amount of resources that's needed to do that and to scale it up, to go from 2 quantum bits to, let's say, 1 million quantum bits that are fully behaving quantum mechanically, you need lots of cryogenics, lots of various laser-related technologies. They cost a lot of money. They're very difficult to implement in general. And I would say what's stopping us is exactly the difficulty of controlling fully quantum behavior. So in quantum mechanics, these superpositions and entangled states are so fragile that if anything else from your environment that you cannot control interacts with your system and learns which state your system is in, that basically is tantamount to collapsing the quantum mechanical state, and that robs you of all the advantages basically that quantum computers give us. So these need to be carefully controlled, carefully isolated systems. People are going down the road of error correction, which means there has to be a huge redundancy. To have 1 quantum bit, you may have to use 100 physical systems just to implement one single bit of information. So it seems to me these are, as I said, with high temperature superconductors, these are largely questions of engineering and having enough resources given to these enterprises. But in my mind, there is no doubt that this will happen one day. The experiments that I have in mind are much simpler than making a unit. Because remember, when you're making a universal quantum computer, you really want to demonstrate that you can make any physical transformation on these 1 million qubits. You can make any quantum mechanical state that you desire, and that's what universality means. For my experiments, I'm aiming at making very specific states. So while, for instance, I can entangle two masses or I can entangle two living systems, it doesn't mean that I can compute anything I like quantum mechanically with this. So they're very specialized systems. And in that sense, that's why I'm even more optimistic. If you think that, if you extrapolate the current trend, and if you think that quantum computers may be here with us within a couple of decades, then I think the experiments I have in mind are definitely closer than that. And that's what makes me confident. So I don't think there are any fundamental aspects there that would prevent us. I think it really is the question of how do we isolate the right kind of system for long enough that actually we can detect the full quantum behavior.
Now, many physicists argue that quantum theory breaks down when we scale it up, correct?
Yes.
So from microscopic to
Yes.
macroscopic.
Yes.
I know this is the same for parallels, and I'm just thinking about polymers and temperature and thickness of materials, even for folding things. But you take the opposite view,
Yes. Yes.
and it's that quantum theory is still the right foundation to build on. You mentioned something like our best current understanding of the universe comes from quantum field theory.
Yes,
And without that, we couldn't account for many of our experiments.
yes.
Why are you so confident that quantum mechanics isn't the end of the story, but the beginning?
Yes, it's a very important point, and it's part of this intuition that, we are all trying to anticipate the future of physics and which way this will go. And that, of course, in our biases, in a way, inform us about what kind of experiments we really think are the important ones to tell us, to distinguish between these different possible ways in which physics can go. So certainly what gives me great confidence are two things. One is simply the experimental progress that I mentioned, that's been extraordinary, that people, in fact, if you look at the latest Nobel Prize in Physics, it was even described as a verification of quantum effects such as quantum tunneling at the macroscopic level. So these are people who took electrical circuits in which you would think that electrons should just obey the usual, Ohm's law, Kirchhoff's rules, whatever else it is that we learn in high school physics. However, what they actually show is that electrons can exist in many different places and many different states at the same time. In fact, they are fully quantum mechanical. So the classical laws like Ohm's law, they break down. And the Nobel Prize for Physics was exactly for showing, this was 50 years ago, in fact, these experiments showing that they uphold even at this level. So the technological progress really gives me the intuition that I think we should be extrapolating and we should be taking quantum mechanics seriously and into the macroscopic domain. But there is another reason, actually, which is purely theoretical, which strengthens this belief that I have. And the reason is the following. People who, as you exactly pointed out, there are people who would say that at some point, at some level of complexity, maybe the size of your system, quantum mechanics will actually collapse and it will return to some kind of classical physics. So they propose a kind of a hybrid view of reality. Below certain scales, it's all quantum mechanical, and above this kind of scale, it would be fully classical, return to some kind of classical physics. Now, theoretically, the problem I have with this is that it's extremely difficult, I would actually say impossible, it's extremely difficult to combine classical and quantum laws together into one coherent theory. And the reason is that they behave completely differently. So, for instance, if you want to implement principles like energy conservation or momentum conservation in classical mechanics, you are using a completely different mathematical structure, a completely different group, if you like, as a mathematician would call, than if you do these kind of things in quantum mechanics. And if now you have laws which are half quantum, half classical, you have no way of unifying this and making it on an equal footing, applying the same treatment, because half of your laws now obey one mathematical structure and the other half obey a different mathematical structure. And in fact, I have something even stronger to say about this. Every time you hear a person say that there is a paradox in quantum mechanics, when they say, oh, this is paradoxical, this can't be like this, I claim that this is always because they're using a hybrid picture of reality. It's because they don't acknowledge that the universe is fully quantum mechanical. So in fact, all our paradoxes so far in quantum mechanics, what people call non-locality, what people call Wigner's friend, even Schrodinger's cat, all of these are related aspects. They are only seemingly paradoxical to us because we are using double standards.
Yep.
We are describing small systems with one logic, and we are describing large systems with a completely different logic. And no wonder you can't put them together. So actually, both experiments so far and this kind of mathematical structure of our theories are telling me that we should really treat everything quantum mechanically. So the way we think of why certain things are as good as classical for all practical purposes, what it means is that as the system becomes larger and larger, it simply interacts more strongly with its environment. And so what that means is that the quantum features become harder and harder to detect. So they're still there, but they become more and more concealed, which is saying that if you take this limit of quantum mechanics, you will actually even recover classical physics. So there's no need to postulate a hard boundary. Quantum mechanics already explains, if you like, it already contains
Yep.
classical mechanics as a special case.
So you think that quantum information just opens up new avenues for these experiments?
Yes.
Now, ones that are technologically feasible but unexplored? What kind of, I'll just say, inertia holds the field back?
It's a great question, actually. That's something that sometimes goes beyond physics in many ways. I think it's partly to do, and that's what I'm trying to, that's why I think I spent quite a lot of time in the early chapters of my book just to set the scene and to all quantum picture of the universe, because I think frequently what's holding us back is our views of quantum mechanics. So these interpretations, even when you cannot at present discriminate between them, even though they might look currently indistinguishable, they actually are informing you completely differently about what you ought to be testing. And I think so why we are stuck, partly one of the answers to this question is, I think, because we have a wrong set of views, if you like, about quantum mechanics. So that's definitely one reason. But another big reason was simply the lack of technology. We didn't have the right technology. Quantum information ideas already started in the late 60s. Then you had ideas by Feynman, by David Deutsch in the 80s. And even all the way up to maybe late 90s, we didn't have experimental physicists being able to really start to take these ideas seriously and implement them. And it's only, I think, mid-90s onwards that I think experimentalists were at the right level to in fact take this forward. So it's partly, I think, we're stuck with wrong interpretations of quantum mechanics, and partly there is a genuine kind of problem with having sophisticated enough technologies to test these ideas.
So let's look into the future with some of the testing, right? The big hype for everybody is AI.
Yes.
So how do you see that fitting into the picture? And something that I'm thinking about and I've seen as a common theme for mathematicians, for folks in chemistry, and I know this is starting to play into physics. What about lean theorem provers? Can you actually see some of that being applied for some
Yes.
of our next laws of physics?
Yes, it's a great question. These are two different directions in which you could be using AI,
Right.
and I think that's very important. One thing to be said is that, for instance, the experiments that I mentioned, where I would like to test the quantum nature of observers. These observers, of course, must be entities with which we can communicate. So, you could do
Sure.
experiments with cats, as Schrödinger proposed, but it's very difficult to ask a cat and to get a definitive answer whether the cat sees, an atom in one state or another, which is why you automatically think, okay, maybe I need a human observer inside. But in fact, a computer would suffice. An AI would simply be, and why am I saying an AI? Because they could be much easier to control in a quantum mechanical way than humans. Humans are probably far messier. You can have an artificial intelligence computer possibly with a much smaller number of bits, which would have all the relevant degrees of freedom that are needed for an observation. All you need really is to get an answer from artificial intelligence about the question of, do they see a definitive answer? So you're looking at a quantum superposition. Do you see anything fuzzy, or do you see that the system is in a definitive state, state 1 or state 2 or any other state that you prepared? So it's a very simple question that the AI needs to handle. So that's definitely one aspect in which AI would be useful. But what you pointed out is, in fact, what about the things that AI could do if it was fully quantum. So the things that we design AI to do, to perform different tasks,
We know
especially
it's coming.
it's coming, and I think I'm certainly a strong AI person, in the sense that I think ultimately we are nowhere near, it seems to me, replicating the way that our brain works. But I think even that is probably a question of time. I don't think that the brain does anything else than some kind of a physical computation. Maybe the current model of computers is not the right model for our brains, but I don't think it will be anything beyond computation. So somehow you could automatically think about speeding up all of these tasks, because now you're talking about this massive parallelism that quantum computers give you. And I think it would be a huge addition to artificial intelligence. The last thing maybe I should emphasize, which is really the exciting thing, and it's the lesson we learned in quantum information. And the lesson was very simple. When you have a new theory of physics, you also have to update your theory of computation and the theory of information processing.
Yes.
So quantum mechanics gives us far more, a wider range of possibilities than classical information. And now the portals that I'm talking about in my book might lead us really into a genuinely new theory, into a theory which actually supersedes both quantum mechanics and general relativity. And it reduces to these two theories in the same way that we were talking about quantum mechanics reducing to classical physics. So it should be all-encompassing, and it should be consistent with our theories if we take the appropriate limits. But for information processing, this is extremely important, because this new theory is therefore bound to be more powerful than either of the theories that we have at present. So to me, what's exciting is to try to even contemplate what kind of computation would this new theory, new fundamental theory of physics, give us.
Now, you talk about portals in your book. Do you want to briefly go into that? And you talk about the idea of portals suggesting more than just a new theory. It suggests a new way of being. So what kind of
Yes, that
reality
is great. Yes.
what kind of reality are you inviting readers to imagine on the other side?
Yes, that's what's interesting, actually. I mean, one can only speculate, of course, and I think usually you get much more surprised from the new developments than what you can anticipate. You know, usually we get somehow positively surprised that there is a lot more, in fact, than we could see, and that's not a surprise, of course. Once you have a new theory, only then can you really properly develop it and apply it to everything else. Yes, I call them portals precisely to combine this idea that it is technology driven and the technology is now at the right level, but they're really taking us, all of us, into a new reality, and not necessarily just a new theory of physics. So what I imagine at the end, and I think this is prompted by the fact that I think whenever I talk about these ideas related to quantum mechanics being correct at the macroscopic level, almost immediately at the end of my presentation, I get a question: what does it mean for us as human beings? What does it really mean for me personally? What are you telling me? So I tried at the end of the book to speculate a little bit about what I think this could entail. And I was inspired, like many of us, by Huxley's The Doors of Perception. Of course, Aldous Huxley lived in California, right, at that time as well. And I think he was advocating experimenting with drugs in a way to broaden your perception. So he thought that our perception is extremely, and if only we could somehow open these doors to a wider perception, we could see the world as it really is, according to him. And he thought it was infinite. So the way I presented this in the book is that I thought that quantum technologies could actually help us with this much more than drugs. I think it's a much more potent form of a transformation, if you like. It's based on physics, not on chemistry. And the idea is that it's possible that the way that our brain engages, which is how I was presenting it as well in the book, it's a exactly technological trip. The way that our brain could really work is that quantum numbers that characterize our perception. And by the way, we still have no idea experimentally what these things are. But one imagines that there are certain ways of encoding information in the brain, which is very similar to how information is encoded in other quantum systems. And that's kind of my thesis in the book. But what this means is that when you interact with your environment, you really are looking for interactions which give you definitive outcomes. So somehow you end up in these crystallized classical realities, because
Yeah,
every time you engage with reality, you see one outcome or another, but you never see anything fuzzy in between. And to me, that kind of signals a possibility to go beyond this kind of binary Boolean logic of our
exactly.
perception and make our perception a bit more flexible in the quantum mechanical way. And what would that even mean? So I of course stop there, because it's difficult to even imagine what kind of perception that would be. But it seems to me that this kind of integration of quantum technologies with our perception is the way to go. And I think this will capture these portals that I'm talking of.
Is there anything that you wanted to add that we haven't covered?
Absolutely, it's great. I don't have anything. Maybe one other thing, and you can put it in. I think if you find it interesting, which I thought now as we spoke, and I didn't mention it. It seems to me that sometimes our obstacles are also the ways in which we fund science these days. So that's something that's hotly debated. Um,
Yes.
in not just in my academic community, but much more
This
frequently
is a
outside.
global issue
It's a
that
global
we're
issue.
having.
It's a global issue. And in fact, many people, Michael Nielsen comes immediately to mind. Many people would say that we are stuck, not necessarily just because it's our understanding of the theory and technology, but in fact, we are largely stuck because people are not adventurous enough to fund risky projects of this kind. And we seem to be stuck with a lot of incremental research, research that somehow is almost clear that it's not risky, and it's clear that it will just confirm what we already know. So there is that aspect as well, which I think obviously goes beyond physics, and it's certainly not my area of expertise, but it seems to me that quite a few of my colleagues would agree with this statement, that there is a lot of waste related simply to how we fund science, and I think we could do this in a much more adventurous way.
As you've heard in today's discussion, the book Portals to a New Reality reminds us that physics isn't finished, and it's just waiting for us to ask new questions. It's a book about imagination, courage, curiosity, and about the strange and beautiful truth that every answer we find only opens another door. You can find Portals to a New Reality wherever books are sold. I'm Autumn, and this is Breaking Math. Until next time, keep asking impossible questions and stay curious. And now a message from our sponsors. What is the Curiosity Box? It's the world's first subscription for thinkers created by Vsauce, the science network with over 23 million fans. Each season brings a new adventure in science, puzzles, and exploration, packed into a box designed to ignite your curiosity. The new box, a showcase of imagination and discovery. Try the 4D tape measure, part ruler, part pendulum, that measures both space and time. Play with Mr. Wiggle's giggle jiggle siphons, silly looking straws that secretly reveal the physics of fluids, and snap-on slap bracelets that double as rulers, cylinder measuring tools, and even tongue-in-cheek time-traveling credentials. Every collection is unique, filled with limited items you won't see again. Subscriptions start quarterly at $75 or $280 annually for even more savings. Subscriptions start at $75 quarterly or $280 annually for even more savings. Available across the US, Canada, UK, Europe, and beyond. Check out thecuriositybox.com/breakingmath and get your first box and get 25% off your first box with the code BreakMath25. The Curiosity Box, because discovery should never stop.